Chapter 20, College Physics, OpenStax textbook, chapter summary. Here we go. So the title of this chapter is Current, Resistance, and Ohm's Law. So I put that up there so it's official, so we know that we have to do those things. And let's just start off. We want to start off with the definition of current. And I'm going to go ahead and write that down. But it's not going to make as much sense until we start talking about matter. So current is defined as the rate of flow of charge. So if I have moving electric charge and I take the charge in coulombs, in time in seconds, this is an amp. So we measure current in amps, and it is the rate that charge flows in a material. Now, let's just look at a material. Suppose that I have a piece of metal, and I can represent that metal very simply as some atomic cores with electrons. So maybe this is copper, and in copper, each atom, the nucleus is essentially in the same spot. They're in it's a solid. But the outer electrons in each atom are able to move to other atoms. And that's what makes this a conductor and not an insulator, is that those electrons are able to move. Now let's consider what would happen, because we did this, if I apply an electric field. So suppose there's an electric field inside of here going that way. Well, the atoms can't move, right? The copper can't move. But the outer electrons can. So all of these electrons are going to experience a force pushing them this way. And they're going to speed up and move this way. But then what happens, I'm just going to draw these extra electrons, they end up over there. And now we're left with some unpaired protons or cores over here. 1, 2, 3, 4. I should have one more. These charge separations create an electric field like that. Well, there is still that electric field. So the total electric field inside of here is 0. So when you apply an electric field to a conductor, the charges move in such a way that they produce an electric field of 0 inside of there. But we call this electrostatics. I'm going to put it in 2 lines. So we're assuming that charges can move, but they do so very fast, and they end up in some static equilibrium position, such as this. Okay, so, but imagine we go back up to our conductor up here and apply an electric field. What if I did the same thing, and I get those extra charges over there, but then I took them away? So I did not allow those charges to build up on the end. Then we would get an electric current. But imagine what each one of those, we're not going to have charges build up, so there's not going to be a cancellation of electric field. However, with a constant electric field, there's going to be a constant force on each electron, and they would do this. So if I draw the velocity as a function of time, it's going to speed up. Because remember, forces make things increase in speed. But they don't keep speeding up. Those electrons will interact with other material, and then they'll slow down, speed up, slow down, speed up, slow down, speed up, slow down, like that. And so we get some average velocity. We call that VD. And that's called the drift velocity. It's important to remember or to realize that that drift velocity depends on the value of the electric field that you apply, but also the properties of the material. So this isn't in the chapter, I don't think, but we should be able to write the drift velocity is some electron mobility. It's a constant, multiplied by the value of the electric field. So if you change the material, this would change. But if you increase electric field, you get a greater drift velocity. But still, in most metals, this drift velocity is actually fairly low. It's not speed of light stuff. I mean, they're not going super fast. But it doesn't matter. But we have the electrons moving, and if we just take those away, then we can keep on moving. Of course, we're going to have to add extra ones in here. So we're going to take these away on this side and add them on that side. And that is change in charge. And how often does it happen? That's delta T. So this is an electric current. And I think that's the really big thing here, is that electric current has to depend on an electric field in the material. And we're going to use that because when we get to Ohm's law, remember that we define this. If I have a constant electric field over some distance, then I get a change in potential. So there is a relationship between those two things. We're going to come back to that later. So that's my definition of electric current, the change in charge per unit time. It's measured in amps. And in most materials, not all, but most of the time, it's actually moving negative charges. Later, when we look at magnetic forces, we can show that we know that to be the case, but here we can just say that's true. However, negative charges moving this way would, in most situations, look the same as a positive charge moving that way. And so we call current the flow of positive charge. Even though they may be going this way, this would be a current going that way. Okay, I know that one's weird. That's just a leftover from the past, right? We picked this to be current as positive charges before we knew that it was negative charges moving in most cases. So, whoops, don't want to change, don't want to admit our mistakes, which is true for most cases. Okay. Now, let's consider two wires. The important thing is that drift velocity depends on the electric field that's applied and the properties of the material. So now imagine that I have two wires. They're the same length, they're the same material, but this one has a cross-sectional area A, and that has a cross-sectional area 2A. So if they're the same material, same electric fields, then they're both going to have electrons moving, let's say, with the same drift velocity. I'll just put one right there. They have the same drift velocity because the same electric field, same electron mobility. However, this is a much wider wire. So over here, I'm going to get more atoms coming out. So the current depends on the cross-sectional area of the wire. In fact, it also depends on some other properties. It depends on the value of the charge it's moving. This is an electron. It depends on how many electrons we have per cubic meter, and it depends on the drift velocity. So we can write this, I equals, I'm going to write the same way they wrote it. Yeah. N Q A V D. So this is the number of carriers per cubic meter. How many free charges I have per cubic meter. This is the value of the charge carrier. And this is the cross-sectional area. So if you increase the area without changing those other properties, you're going to get more current. If I double the area, with the same drift velocity, I'm going to double the current. Now, we're going to see also that changing the length has an impact too. Okay, I'm trying to stick with the book here. Okay, that's drift velocity. So there's a current. The drift velocity does depend on the electric field. Okay, remember that. And so we can get this relationship between the current and the electric field, which depends on the change in potential. So I'm going to write this, which the book doesn't do. I equals NQAUE. Instead of the drift velocity, I put the electron mobility times electric field. So suppose that I do have an electric field in here, E, and this has a length L. Then I want to find the change in potential across that wire. I can say delta V is negative E times L. Well, it turns out that I can write E in terms of I. I know this is a little weird, but I'm going to do it my way. And let's just talk about the magnitude here. We'll talk about the direction soon. I can write this as E, which is going to be I over NQAU, right? That's solving this for E, and then I get L. But you'll see here that that's the change in potential across the wire, that's the electric current, and these are all properties of the wire. And so we can write those properties of the wire and call that the resistance. In units of ohms. So the resistance, but then I get delta V as IR. I get this. Now, we're going to drop the delta V a lot of times. It really should be there, but that's where that V equals IR comes from. Remember, potential is always a change in potential. You can't, especially in circuits, you measure from one point to another. There's two wires in a voltmeter. Oh, here. No, I was going to grab a volt. I have one right here. Voltmeter, it's on one. Two wires. There are two wires in a voltmeter because it's a change in potential. Okay, we'll talk about measuring those things later. Okay, so that's V equals IR, and then R is going to be this, L over N, L over N Q U A, I put it that way, because L and A are properties of the size of the wire, NQU are properties of the type of material. And so we can actually write this as rho L over A for a wire. So this is the resistivity, which is just depends on these materials right here. So a longer wire has a greater resistance. A thicker wire has less resistance. And it's because the resistance tells you the current per voltage. And here, if I have a wider wire, I'm going to get more current. So therefore, lower resistance. Okay, that was a lot. Okay, but it was important stuff there. And so that is Ohm's law right here. Delta V is IR. Now, I do want to point out one thing again. Let's switch to a very basic circuit. Okay, we're going to look at circuits here. So we're going to have current, voltages, and resistance. I'm going to show you how to draw these. So I'm going to draw a battery like this, and a wire, and a resistor. So for the battery, we draw them as a long side and a short side. The long side is positive and the short side is negative. That's just our convention. And I'm going to call this VB for the voltage across the battery. Some places call it an EMF. That's fine too. So the conventional current I will come out of the positive side and go through here. We're going to get into this later, but we can use two very important ideas. If you remember that delta V is negative E delta S, that's how we define the change in potential, and came from the idea that we could turn the electric force into a potential energy. We can do that if it does not depend on the path, which means that the work around a closed path has to be zero. So here we can use that same thing, right? If the work done around this closed path is zero, I can say the voltage across the battery, I'm going this way, VB, and that's going to make an electric field going that way. Now right here I'm going across this, but I'm going in the same direction as the electric field, so it's going to be minus IR, that's my Ohm's law, and that's going to be equal to zero. So I get VB equals IR. So the voltage across the battery would be the current passing through the resistor times the resistance of the resistor. And we will do more complicated circuits later, but that's where you need to know what we are doing right now. Okay, I skipped something. I got to go back. I had this R rho L over A. The resistance of a wire depends on the resistivity, the length, and the area, the cross-sectional area. But the resistivity isn't always constant. We can also say the resistivity depends on the temperature, as this. So as I increase the temperature, A positive change in temperature would mean that the resistivity would increase too. The resistivity increases with temperature, so the resistance increases with temperature. And in this rho 0, this is the Greek letter rho. Rho 0 is the resistivity at temperature T0, whatever that is. And then T would be the final temperature. So you could write this as rho 0, 1 plus alpha T minus T0. So that's the temperature that goes with that resistivity. Call it room temperature if you want. And then alpha is just a resistivity coefficient that depends on the type of material. It's just a coefficient. This is an important thing too. If you increase the temperature and the resistance increases, if you decrease the temperature, resistance decreases. And you've probably heard of them before, but if you decrease the temperature enough, for some materials, their resistivity goes to 0. And when that happens, we call that a superconductor. We're not going to study superconductors in here, but it's important to have some connection with reality and cool stuff too. So a superconductor is a material with 0 resistance. Normally, you have to keep them very, very, very cold. So you use liquid nitrogen, liquid helium to keep them cold. The idea would be if at some point in the future we could get room temperature superconductors, that'd be pretty awesome. Okay. Let's talk about power. Remember, this is a summary. This is not everything, right? I'm summarizing stuff. So from physics last semester, we had power was the rate of change of energy. That's my potential energy there. I'm using U for potential energy. And if this is in a joule per second, then we call this a watt. Okay, so imagine that I have charges in a wire and they're moving. So some charge Q and it moves over some change in potential delta V. In that case, the change in potential would be Q delta V. We saw that before. So I can write P as Q delta V divided by delta T. Now, what if I just group the Q that moves with the delta T? That's current. That's electric current. So I can write this as IV, and that is my power. So the power through some element is the current multiplied by the voltage. Now, and I shouldn't say voltage, okay? Just like I shouldn't measure distance in meterage, but I do. Everyone else does too, so we're all bad people. If we're all bad together, it's fine. Since V is equal to IR, I can write this as I times IR, which would be I squared R. So you could write it that way too. Also, I could write I as V over R. So I could write this as V squared over R. So those are all the same definition of power. If your potential is measured in volts and your resistance in ohms and your current in amps, then those all give you units of watts. This comes to something really important. There's two things, right? If you look at a battery and it has a label on it, it'll say something like delta U is 720 kilowatt. I'm making up a number here. Kilowatt hour. That is a unit of energy, okay? Because a kilowatt is watts, which is joules per second, and I multiply it by time, I get energy. So if you want to convert this to joules, this would be equal to 720 times 10 to the third watts times hours. But I need to convert the hours to seconds, so if I multiply 3,600 seconds per hour, right, because it's 60 minutes times 60 seconds is 360 or 3,600 seconds. The hours cancel, and I'll get watt seconds, and a watt second is a joule, so you can convert that to joules. So that kilowatt hour is a unit of energy, not power. Okay. The other way you'll see energy on a battery, and I think like the iPhone batteries and the phone batteries do this, like 7200 actually, maybe not, mAh, milliamp hours. And so that's not technically a unit of power, but you can find it. Because if it's milliamp hours and you know the potential, so some of these batteries are, let's say, 3.7 volts. So if I take 3.7 and multiply it by, convert that to amps and multiply it 3.7 times the current, I get the power, and then I convert from hours to seconds, and you can get it to joules too. So if they list it in milliamp hours or amp hours, you have to know the battery voltage in order to calculate the energy in the battery. They have a section in there also about the cost of energy. Normally you pay per kilowatt hour, but remember kilowatt hours is a unit of energy. You probably want that in joules. So you have to multiply by 3,600 to get it to joules. Alternating circuits. So we have this. I was going to bring a demo, but I didn't. This is a DC circuit. Direct current. It means that current flows this way, and that's it. So a battery has a positive side and a negative side. There's a wall outlet down there. It's actually got 3 plugs. But imagine it just has 2. Which one's positive, which one's negative. And yes, there's a live and a not live, but in general, those are alternating circuits. And we can write those as, instead of a battery, we would write it like this. So if I plotted the voltage of the battery as a function of time here, it would look like this. And let's say it's a 9-volt battery, just like that, constant. If I did it for this one, it would look like this. It doesn't have to, but it usually does. So this is what we call an oscillating current. There are a couple of important properties of this. Let's assume that it's a sine wave. It doesn't have to be. We have here the amplitude. We'll call that V0. And then we have the time it takes to make one oscillation. We could call that T. And if we take 1 over T, we get the frequency in hertz. I can mathematically write that function voltage as a function of time. It looks like this. V0 sine omega t. So that's the Greek letter omega, lowercase omega, and omega is equal to 2 pi times the frequency. But this is in radians per second. This is just easy. The book actually just leaves it as 2 pi f, but I like omega better, and I'm going to do it the way I want to do it. But here we have an alternating voltage. If I run that through a resistor right here, well, as the voltage moves back and forth, you can see it's positive and negative with an average value of 0. If I let that go back and forth, the current's going to go back and forth too. So we'll actually have the current looks like something similar, maybe a different amplitude because it's different units. I can use that to calculate the power as a function of time. It's going to be I times V. But this current, I, as a function of time, would be I0, the amplitude of the current, sine omega t. Now, this is not always true. AC circuits can do weird stuff, but we're doing not weird stuff right now. So if I multiply these two functions together, I get I0, V0, and then I get sine omega times sine omega t, and that's sine squared omega t. And you'll notice that since it's squared, it's always a positive value. And in fact, it looks like this. That's the power. It's always positive. If we average this function, sine squared, which you'd have to do with calculus or do some other trick, but the average of that function is a half. The average of sine is 0, right? Because it's as much positive as it is negative. That's always positive. Has an average of a half. So we can write this P average as I0 V0 over 2. Now we can do something fun. So my average power is I0 V0 over 2. I want to take half of that 2 and go with the I, and half of the 2 and go with the V0. So I can write this as I0 over the square root of 2, V0 over the square root of 2. Right? Because square root of 2 times square root of 2 is 2. So it's the same thing. Now I can call this I0 over the square root of 2. I'm going to call that I RMS. That is the root mean squared of the current. It's a way to describe the average value of the current, which is actually 0, but describe that it's not 0, right? Because the current's going to be as much positive as negative. It's going to have a 0 average. So the RMS is not 0. It tells you something about the current, though. And the same thing for this. V0 over the square root of 2 is VRMS. So when you measure AC currents and AC voltages with your voltmeter, you're measuring the RMS voltage. RMS stands for root mean square. So it's because we're taking the square root of the average of the square, right? Because that's what we did over here. That's why. Okay. I'm going to end with one thing right here. And that's going to be, which I should be doing in all my chapter summaries, what are the most important equations for this chapter? Right? You want to kind of like keep a chart of all the important equations. So in this case, we have, let's review, I delta Q over delta T. That's the definition of current. I have this one, I equals NQA drift velocity, and my bonus, the drift velocity, is the electron mobility times electric field. I really like that one. Then we have Ohm's law, delta V is IR. If you're going in the same direction as electric current, that's a negative change of potential. That's important, right? Because the electric field is in the same direction as electric current. Resistance is the resistivity times length over area. Resistivity as a function of temperature is some base number 1 plus alpha times the change in temperature. Power, I times V, which is I squared R, which is V squared over R. V is a function of T for AC circuits, is V0 sine omega T. I is a function of current of time, is I0 sine omega T. And V RMS is V0 over the square root of 2. I RMS is I0 over the square root of 2. And then average power is I0 V0 over 2. That's it. Chapter 20. I'm stuttery now.